pleasure to be here and to talk about my research and see also familiar faces. And I hear some of my collaborators were here a few weeks back, Subhashish Mitra, so some of the things that I'll be talking about are related to also the ideas that he was describing, and in particular in the first part of my talk. So let me start with some of the work that my group has been doing on optimized photonics. And in the first part, I will primarily talk about our classical photonics work, where we would like to introduce optical interconnects to reduce energy consumption or build neuromorphic processors and so on. And then in the second part of the talk, I will talk about quantum computing. But there is a common theme, and the connection is really through photonics. So for start, let me show this slide, and some of you may have seen these results recently. On the right-hand side, we have on-chip optical interconnects. This is the work by Berkeley and also MIT, where they replaced connections, on-chip connections, on-chip copper wires with optical connections, and managed to perform operations at pretty high speed and so on. And then on the left, we have optical neural network, which is the work from MIT by Dirk England, who was actually my former PhD student, and Marin Sojocic. And they built these silicon photonic circuits and showed that they could essentially use this as a very small-scale optical neural network or neuromorphic processor. But although these are really beautiful demonstrations and show you some of the emerging applications for photonics, there are actually problems with this. Most notably, the state-of-the-art photonics that is used here, and you can already recognize some similar elements in both of these demonstrations. The state-of-the-art photonics is very lossy, right? So people here, for example, for these optical interconnects, replaced copper wires with optical connections that occupy much more space and are more complicated. But at the end of the day, they consumed on the order of a picojoule per bit. And that was the same as the energy consumption that you would have if you were just transmitting your electrical signals down the copper wire. So it was really beating the purpose of using optics, because you were not really saving in energy at all. And the idea is to really introduce optics for optical interconnects so that you can ramp up the operating speed and reduce energy consumption. But unless you are in the range of femtojoules per bit and operating at speeds greater than 20 gigahertz, you are not really gaining at all. So that's where the problem is with the state of the art. Also, all of the optics used here is bulky. I mean, you don't really have scale bars at most of the pictures, except here. You see 50 microns. And this is one of the filters that they're using in their structure that is just filtering one particular color of light that is used for communication. And you need a lot of these colors or wavelengths for communication between different channels. But each one of them occupies about several tens of micrometers. And of course, that's way bigger than electronics components. So you have to spend a lot of real estate on your chip on optics that is lossy and large, and that's not really where we would like to be. And finally, all of the optics used here and in other state-of-the-art experiments is very sensitive to fabrication and temperature errors. So if you're off by nanometers, or if the temperature of the electronics nearby changes by a few degrees, you're completely off your operating point. For example, this filter would then filter a completely different wavelength, and if you would like the system to work, then you have to tune it. And the way people tune these systems is through these integrated thermal tuners or heaters, and you see them here, you also see them here, and they're extremely lossy because you have to heat the system up to compensate for temperature differences. And that's where the main source of loss is. That's what eventually brings the loss to picojoule per bit operation and to the regime where your electronics is. So for many years, my group has been looking into a lot of these applications and systems. And if you zoom in into individual components, you again see the same trend. They're very large, right? This is one of your filters. Designs are more or less very regular, right? Shapes are regular. Nothing very surprising here. And the reason why all of these components are not working as well, we thought, is because we never really optimized them or designed them right. We just use optical devices that have been around for many decades. We adopted them in many cases from microwave engineering. We did some fine tuning and tweaking of parameters so that they work well enough, right? But then when you put them in the real world environment and try to integrate them with electronics and everything else, or if you try to fabricate them, there are always errors. They're not really robust to any errors or environment, and they don't really work that well. On top of that, you need optics expert to design any of these systems, right? And now when we're in the stage where we would like to integrate optics with electronics, electronics designers cannot really design optics. You need someone who has worked on optics for a long time, who knows this very well-known library of components, and they can take them and tweak them and try to combine them with electronics. But that didn't really seem to me and my group members like the approach that would be sustainable or work in the future. And clearly, this is not how we came up to integration of all of many billions of transistors on a chip, right? We need some more systematic design where people without extensive expertise can design a system and where components are robust to errors and you don't need to post-tune them and so on. So we decided to explore that further, and we came up with a list, a wish list of requirements that we would like to have for our new optical devices and components. So we started wondering whether we could make better optical components, smaller footprint, robust to errors, robust to temperature variations, systems that are not really sensitive to a nanometer of fabrication error that you, of course, have to experience during your fabrication process. Can we also come up with new functionalities beyond the existing library that we just have been using and recycling for decades? And could we actually eliminate this brute force design and manual parameter tuning from the design process? Because that's not really how people design electronic devices. And after a lot of years of work in this area, we think that the answer is yes. And 5 years ago, we came up with the first breakthrough where we managed to design actual practical optical devices. And even if you're not experts, if you look at this here, you see that it looks very different from the structures that I showed you on the previous slide. So the geometry is very different, but it is actually a result of computer optimization. So we thought that the only answer to all these questions is to try to find really optimal designs for a particular function. And optimal designs beat our intuition. They're not really like the designs that we were taught to analyze or use at school, because those designs adopted from 30, 40 years ago were simply designs that people could solve analytically, right? So there is no really reason to think that a simple ring is an optimal solution for a filter. So this structure here that I'll be describing more later in my talk is a real device. It's in silicon on insulator. It's a two-color filter, right? So it splits two different wavelengths in two different ports, and it does it in a footprint that is 2.8 by 2.8 microns. If you recall, I showed you a state-of-the-art filter, which is a ring on the previous slide, which has dimensions of about 20 to 30 micrometers. So in the footprint of a single filter, you can pack a few dozens of this. And not only that the footprint is smaller, I'll show you in a moment that this structure is resistant to huge temperature variations and large fabrication errors. So you don't really need post-fabrication tuning once you make this and put it on a chip. And of course, this was very exciting to people in industry, but also other people in academia. There are quite a few groups now that are looking into this optimization in photonics and working on it actively. So how do we approach this problem? Right? Yeah, I said at the beginning that the idea here is to eliminate brute force design from the design process, and we didn't want to really keep recycling the same device library with some minor optimizations in building optical systems. Instead, we wanted to design device for a particular function. So let's say you would like to filter out two different wavelengths, and you have to do it all the time if you're making any type of optical processors, because you use different wavelengths to communicate to different channels, right? And let's say you would like to do it in this 2.8 by 2.8 micron footprint. If you would like, you know exactly what your inputs are, and you know what your outputs should be. That's how much you know. But you don't really know what this optimal black box is. And that's what you would like to design and optimize. So how do you approach this problem, right? Well, you can say, I can pixelate this into 20 nanometer pixels or 100 nanometer pixels, right? 100 nanometer pixels are pretty coarse. That's too big and would cause a lot of losses in optics. But let's say you can pixelate it in 100 nanometer pixels. and try all the combinations of silicon and air or silicon and oxide for these pixels, right? And see if there is any combination there that would work as this wavelength filter, right? So that would be potentially an approach that would work. But unfortunately, the parameter space of even for such a small device is so large that unless you are extremely lucky, you will never be able to find the optimal solution. Even for this coarse discretization of 100 nanometers, right? For this tiny device and simple function, you have 2 to the power of 784 possibilities, which is 237-digit number. That is larger than the number of atoms in the observable universe. And remember, you have to try and simulate all of these structures, and they're three-dimensional structures, and simulations of all of them take time. So there is no way in your lifetime you will end up designing an optimal structure, right? And people have attempted this in the past. It may work with moderate success for some smaller structures, but it's not really the approach that would eventually work. So we decided to be smarter about how we approach this. And instead of doing this blind search through the parameter space where you're just flipping pixels randomly and simulating structures, we decided to do some physics-guided optimization. And this is exactly the same type of optimization that people do in other fields, right? But in this particular case, we apply it to the physics problem. And we started collaboration also with Stephen Boyd, who is an optimization expert at Stanford, and some of you may have known him, may know him. So the idea here is still that you pixelate your structure and you analyze it, but the way you are flipping pixel is guided by the physics of the problem. And for those of you who may be familiar with the optimization approaches, we use some kind of gradient descent method where the trajectory that we follow through the parameter space is basically guided by some cost function that we set up. In this case, cost function or figure of merit would be output and input modes, or the overlap of the actual output with the desired output, right? So we would really like to filter these particular colors at the output, and until you get there and you have nearly 100% transmission efficiency in the overlap, you don't really stop. But that's guiding your trajectory through the parameter space, and your trajectory through the parameter space would look something like this. Of course, I'm only sampling particular points during the optimization. You make, in general, about 200 steps of optimization until you reach the optimal solution. But we start with uniform dielectric constant. Then we do what is called continuous dielectric constant optimization, which means that you vary refractive index of your material continuously between air or oxide and silicon. And then you do boundary parameterization, which is essentially discretization. Discretization means that you allow only two materials, oxide and silicon, and that's something that you can make, right? Because you know how to drill holes. Nobody knows how to make this. Nobody can continuously control the dielectric constant or refractive index between two different materials. You may wonder why we're doing this, because this is the only thing that we can make. And the answer is this problem here, parameter space for this has a lot of local optima. The problem is highly non-convex. So the complexity of solving this is much higher than complexity of solving this and then discretizing. So the answer is in optimization. And if you try to optimize this directly, you'll never get solutions that are as good as when you are following this trajectory. And a lot of people have tried this in the past. So let me actually then show you the final result. So here is the final result. Here is what the computer produced as the optimal solution. It transmits one particular color to one output port, the other color to the output port, the other output port. This is how the field patterns would look like, very non-intuitive. If you scan the input wavelength, you see that initially light goes to one port, then it goes to the other port at this particular point. You have around 100 nanometers of bandwidth, which is much more than you have in normal filters. You can pick other bandwidths. We just wanted it to be very large. And it works quite well, and as you see here, transmission is pretty high. I mean, we stopped when it was satisfactory for us, but it could be even higher than what you see here. And although you run optimization for the full three-dimensional structure, we only optimize pattern in 2 dimensions because this is easy to fabricate, and this is something that you need to transfer and etch into your silicon on insulator structure. But the optimization is all done in full 3 dimensions. So once you have that desired pattern, you can take it and import it into your lithography equipment. in this case, we used the electron beam lithography system, but I'll show you some of the other approaches later on. Then you transfer the pattern directly from your computer into the lithography system. You write that pattern in the polymer. Then you use it as a mask for etching, transfer into silicon, and eventually we cap everything with insulator, but I'm not showing you cap structure so that you can see the pattern here. So everything will be filled up with oxide so that you have the structures protected. So this is the actual device, silicon sitting on insulator, fabricated also by us at Stanford, and this is the designed structure. So then more of these designs and fabricated structures. Here is again your actual device. These are just input and output waveguides that we hook up to detectors and fibers. Other than that, all of the action happens here. So we needed long waveguides all the way to the ends of the chip so that we could characterize them. So then we characterize them and measure device performance. So here is the theory for the actual fabricated device. Here is the experiment. And they match very well. But what is the most interesting thing here is that we plot transmission of multiple devices on top of each other without any post-fabrication tuning, and they all line up on top of each other. So this broadened curve here means that you're just plotting transmissions for multiple devices. And this is something that you cannot do with traditional designs. There is no way they would line up unless you post-fabrication tune them and tweak them and use thermal heaters. So there is zero tuning here, and they all work exactly the same. So that was super exciting for us and others, so we decided to continue. And this broadband design that we had also incorporates a lot of robustness, right? So we wanted to study how robust the devices would be to typical temperature variations or fabrication errors. And there is a lot of intrinsic robustness that is incorporated during the design process. So for example, in this case, for the wavelength splitter, this is a slightly different design, but also another wavelength splitter in a different stack. You can change temperature by hundreds of degrees. And at the target wavelengths of 1.3 and 1.5 microns, it still operates as a filter, right? Of course, nobody needs to change temperatures by this many degrees, right? We need stabilities for a few dozens of degrees, but this is exaggerated to show that even something like that could be designed. And in traditional devices, 1 degree temperature change completely throws it off out of the operating point. So that's why you need tuning. And clearly, in our case, we don't need any tuning. What about fabrication imperfections? So if you have 8 nanometer under etching or over etching, meaning that you have all of these features, but they're all smaller or bigger by 8 nanometers, which is a pretty large error, right? That's something that graduate students, that's an error that graduate student can make. And it's not an error that you would typically have it in a company. But even for that type of error, the device still operates pretty well. It has performance that is just slightly degraded at the target wavelengths of 1.3 and 1.5. Again, this is not something that you can have. 1 nanometer errors in traditional devices lead to huge degradation in performance. And we were very happy to see this. So now going back to fabrication constraints, when we started building these devices, we just designed them, and we didn't really worry about our actual fabrication constraints. They ended up being robust because we designed them to be broadband. But when we fabricated them, we realized that some of the initial features at the input of the device were missing, right? After we looked at them in the scanning electron micrographs, we saw that these tiny features, you see them here, were missing, and this is because they were smaller than about 50, 60 nanometers that we could reliably make, right? So 50, 60 nanometers is not a really big hole, and of course, a lot of people can make it, but that's not something that we can reliably make at Stanford. So we said, well, we don't want this to happen to us or to others. We want to incorporate fabrication constraints directly into the design process, which means that you don't want to design something that will have features that you cannot reliably make. And this is our constraint. You can incorporate fabrication constraints of the foundry or your fabrication process, and that also could work. And we did it. In fact, we spent the last couple of years primarily doing this. So as an example, here is how our old spatial mode splitter device would look like, where you split first and second order modes. They have 1 lobe of the field at the input and 2 lobes into 2 different output ports. Not so important. Just look at this complicating pattern here. If you incorporate fabrication constraints, the same device with much more streamlined pattern, right? This is much easier to make. This incorporates our fabrication constraints. And performance, in fact, is even better than for the previous device. It's a broadband 300 nanometer device with very high transmission. Here is another one. This is a 3-way power splitter that splits equally input power into 3 output ports. Here is the designed field pattern. And here is the fabricated structure in silicon on insulator. Here is the simulated performance. It's, again, very broadband, so it would equally split power in 300 nanometer bandwidth, which is a lot. And then here in the experiment, you measure transmission for multiple devices, and they all line up on top of each other. So again, it's very good performance. And as you scan input wavelength, it splits it equally into 3 ports, even if you scan it within 300 nanometer bandwidth. So that's all very nice and fun. Then we kept going. We wanted to incorporate both fabrication constraints and smarter optimization methods into the design process. I mentioned that we first do continuous optimization, but then discretization of the structure, so we end up with something that we can make. And often that process where you just binarize, discretize the structure led to a reduction in the performance because you don't have something that's gray anymore, which is optimal, but you go into black and white. So we wanted to avoid degradation of performance there, and we started incorporating new algorithms, which we call biasing, which basically, even in the stage of continuous dielectric constant optimization, lead to something that's mostly black and white. So there is a little bit of gray, but not as much as if you don't use that biasing as what we did before, which means that when you discretize this, when you make refractive index only air and silicon or only oxide and silicon, it's pretty close to the optimal structure. And here is the device that we optimized using that process, which is, again, 3-color splitter. You split 3 different wavelengths that are closely spaced, 1500, 1540, 1580. This is used typically in communications. Footprint is just a slightly larger than the footprint that we had for 2-channel device. You go from 2.8 by 2.8 microns to something on the order of 3-4 microns in dimension, which is very important because in traditional devices, for every additional channel, you need another 20 by 20 microns component that you have to put on the chip. So when you fabricate this, it looks pretty much like designed because we incorporated fabrication constraints. And then when you measure and plot transmission for multiple devices, it matches theory really well. And again, I don't know if there are optics experts among you who have done photonics or optics experiments before. Doing this without any post-fabrication tuning is really not something that has been possible at a university or even in companies. You have to do post-fabrication tuning to line them up all on top of each other. So of course, we're moving further. A lot of people do deep WDM, deep wavelength division multiplexing communication, where they need more than 3 or 4 channels. So they want to have 10 channels or even more than 10 channels. And just to show you that this is possible with this approach, this is a 10-channel demultiplexer preliminary, where in the footprint that's only about 4 by 12 microns, you split 10 channels. So you're not increasing the footprint by that much. And it's resistant to temperature changes of about 10 to 20 degrees, right? And that's more than enough for putting this system on the chip, but we actually can also make even more temperature robustness. So now, some of you may say, well, this is great, but you're just using E-beam at a Stanford. That's not really high throughput fabrication. How do you really use this for optical interconnects? You want to use real fabrication, high throughput fabrication methods. So we started collaborating several years ago with global foundries on this. And we've made a lot of progress since then, and it's quite exciting that actually you can use standard CMOS fabrication to make our devices. So at first, they looked at our designs, and they tried to figure out whether they can make optical masks for this, and what they're exposing them in 193 nanometer lithography, whether devices would operate as desired. And simulations were indicating that they should work very well, right? And this is how devices would look after exposure and relative to nominal devices. So that looks pretty good, but they were not really made yet at that point. So now, going back to our designs, they also recently came up with photolithography masks, exposed them, and the exposed structures look exactly as our desired devices. And that's the key step. Beyond this is just etching, right? And this is super exciting because it means that you can use standard process, 193 nanometer lithography, even for the structures that we designed using our fabrication constraints. But right now, what we're trying to do is design them using their fabrication constraints because they're slightly different. Anyway, this tells you that you can use the same process, make this right next to your processor, next to all of the electronics, and not really have any problems. You don't really need to use e-beam lithography. It's high throughput. It's very efficient. There are a few other things that I'd like to share with you. If you have done any optics, you probably know that most of the losses also happen at the input of the chip. You have to couple from fiber. Typically, people throw away about 50% of the power. Coupling about 50% is considered relatively good, right? So you have a laser at the output, but you lose 50% of that even before you couple to your optical chip. And then there have been some designs for better couplers, but those designs incorporate multi-layer structures that are really hard to fabricate, so people cannot really fabricate them in foundries or even at universities. So recently, we designed a very good grating coupler with simple one-layer structure and one-layer pattern that couples 97% of the vertically incident beam from a fiber. And this is really game-changing because it would lead to large power savings, and also is something that could be relatively simply fabricated at both universities and in industry. Finally, another thing that we're looking into is design of better resonators, and this is connected more to the second part of my talk, where I'll be telling you about quantum technologies and quantum computing. You'll see some traditional designs of resonators that we and others have been using, but we also wanted to design better resonators. And this is how the design process for a resonator looked like. So start from something that's completely uniform. You ask the computer to design something that would hold on energy, electromagnetic energy, in a very small region of space, and it produces this. And this doesn't look like a resonator that any of us would design. I mean, you see some periodicities. You would guess it's a resonator, but it's not really like a traditional resonator. But certainly, it outperforms traditional resonators in terms of the what we call quality factor and the volume where field is stored. So to finish up this part of my talk, I'd like to just remind you that we came up with the methods that allow us to design photonics to be small footprint, robust, insensitive to errors, and efficient. These are experimental examples of some of the wavelength filters that we designed, and of course, we've done many more. And if you're interested in details, there are a lot of publications that we published over the years from the design part and theory that we've done in collaboration with Stephen Boyd to our first experimental demonstrations, and more recently, fabrication constraints, which is what leads to really practical devices. And although in the past, photonics has looked something like this, right? Very regular structures, kind of boring. Based on everything that we've seen so far, we think that actual photonic devices will look very different in the future, right? Very non-intuitive, but outperforming what the state of the art is. So now I'd like to shift gears and spend the rest of my talk telling you about our work on quantum processors and quantum technologies. And it's not very, it's also very strongly related to the first part of my talk, because photonics is a critical part of all of the quantum technologies. Not only quantum communications, where you want to securely communicate with another party, and you, of course, have to send signal over optical fibers, so photonics is important, but also for computing itself, because ultimately, you have to network these computers. You also need optics interface to the user, right? Because there may be just few of these computers stationed at national laboratories or companies, and then users have to access to it over the internet. But there are also fundamental limitations to how many quantum bits you can pack into each quantum computer, that many people are actually encouraging the idea of using optics to multiplex and interface either multiple machines or to bring more quantum bits into a single machine. So you may have seen some of these pictures, especially this one. This one is from IBM, recent announcement of a 50-qubit quantum computer. Google also made an announcement that was quite recent. This is how their 50-qubit quantum computer chip looks like. This was from Harvard-MIT collaboration, 51-atom quantum simulator. It was not as much in the news because it's atomic physics experiment, right? And it was also not, it was done at the university, not in companies, and a little bit more bulkier and I guess more fundamental, but kind of operating in the same regime, although it's a quantum simulator, not really general purpose quantum computer. But this is very exciting, actually. We live in a very, very interesting era for quantum computing, and a lot of progress has been made over the past couple of years. But there are still a lot of issues. Right? Scaling is extremely, extremely hard. Right? Increasing number of qubits is a really challenging process. And also, these systems are very bulky, fragile. They operate at millikelvin temperatures so that you can isolate them from the environment. If you actually look how this quantum computer looks like, it's not this chip that you may have seen in the news. I mean, this is how it actually looks like, and you need all of these wires and coaxial cables to control individual qubits, and this goes into dilution refrigerator that cools it down to millikelvin temperature. So it's not something that's going to go into anybody's home anytime soon, right? And similar for atomic physics experiments, right? You kind of may see pictures like this, but other than that, this occupies the whole lab, right? This occupies 20-foot optical table, if not even more, right? So scaling is hard. These are bulky, fragile systems. And maybe people even don't care about that much. We'll build just a few of them and use them. But the problem is that there are fundamental limits to how far you can scale, right? And adding each qubit to the system also increases errors. So recently, John Preskill, who is a professor and one of the leading experts in theoretical quantum information, has proposed the idea of focusing on this noisy intermediate scale quantum technology that we already have with 50 qubits, maybe to up to 100 qubits where we can get. And instead of trying to push it to thousands of qubits or millions of qubits, which may not even be possible at this stage in a single computer, just try to network them and try to see what we can do with that, right? Or maybe try to come up with more interesting algorithms and exploit these 50-qubit architectures for something useful. Because at this stage, having 50-qubit quantum computer is not particularly useful. It's still not good enough to run any useful algorithm, such as factoring algorithm, Shor's algorithm. You can only run quantum simulations that are interesting for physicists to show that this is advantageous relative to classical platform. And this may resonate with a lot of you. This is a picture from my colleagues, Mark Horowitz and collaborators from a while back, looking at the classical processors. You probably remember that in early 2000s, when the performance of a single core processor started to taper, to saturate, people started actually putting more and more logical cores. And that's when we gained in the performance, right? So we couldn't really make individual processors significantly better, but we could network them together and gain from networking and multi-core architecture. So that's exactly the same idea that John Preskill is proposing here. Let's use what we already have, 50-qubit architectures, and connect them somehow and gain from the connections. So how do you connect them? All of these systems are superconducting systems operating at millikelvin temperatures, and you build them in individual dilution refrigerators. If you want to connect them, you need to have optical connections. So it's absolutely critical, both for interconnecting them into some multi-quantum processor core architectures, but also for building a quantum network, long-distance quantum network, or quantum communication system, that you have optical connections. And this is a picture from Chris Monroe. He's at University of Maryland, where they proposed to connect ion trap-based quantum computers and connect them optically, but the same idea could hold for any other quantum computing architecture. So you have sort of classical optics, quantum light sources, and quantum computers that are processing information locally. So in addition to that, right, in addition to optics playing an important role in the connections, we're also thinking about whether we could come up with better material systems that would lead to quantum processors operating in friendlier environments, right? And by that, I mean maybe not room temperature, as shown here for my student Linda, who is here at Google Science Fair showing our Diamond quantum processor, or components of quantum processor, but something that could operate maybe at temperatures of 4 to 10 Kelvin, where you have much better, much easier to use closed cycle cryostats. And some of the platforms that I'll describe in a moment that my group is pursuing, and also other groups, include work on diamond and silicon carbide. So not silicon yet, but group 4 semiconductors, where you can use standard microfabrication, more or less, and you right away have optical interfaces. So you don't have to worry about converting microwave photons to optical photons to interconnect the systems. So what are the candidates for the other systems? Well, this table, something that I usually like to show. This is something that my students and postdocs and I collected for a while. And this is essentially the state of the art in quantum hardware, right? Google IBM quantum hardware is based on this circuit QED, superconducting circuit. So that's the first column here, right? This is from Copenhagen, Charlie Marcus. They are right now closely connected to Microsoft Station Q, right? So this is a very similar platform. This is ion trap-based quantum computer that I showed before, very similar to atomic systems. And this here shows pictures from my group, but there are, of course, many other groups working on semiconductor systems. This is 3-5 gallium arsenide, this is diamond, and this is silicon carbide. So this table contains a lot of information. You don't have to read everything, right? But I'll just emphasize a few important points, right? The bottom half of the table is what you should pay attention to, right? Fidelities are probabilities that a gate works, right? And of course, you want this to be 100%. And there is a lot of work out there on quantum technologies where probability of the gate is 50%. That's never going to work, right? You connect multiple gates, probabilities multiply, so you're never really going to build it into something useful. So you clearly want this number to be in the 90s, as close to 100% as possible. And in particular, that holds for 2-qubit gate fidelities, which are non-trivial gates. It's not just rotation of a single quantum bit, but equivalent of AND gate for 2 quantum bits. Then what is also important is how many of these 2-qubit operations you can do before the system decoheres. Quantum systems have to be isolated from the environment. Eventually, they lose quantum mechanical properties. That's what we call decoherence. The duration for which you can run your quantum algorithm is limited by how many operations you can do before the system decoheres. So that number should be as large as possible, right? And also, you want the system to be scalable, right? And also, you want it to have optical interface, right? Because otherwise, you cannot network it. So if you look at this table, these are the systems that have done the best so far, circuit QED systems. They have pretty good fidelities, right? Excellent fidelities, more than 99%. Number of 2-qubit operations is not that large, actually. It's about 1,000. They're trying to push this, but they're not there yet. The systems are scalable. They're lithographically defined, and they don't really have optical interfaces yet, so people are actively working on this. These systems here, based on gate-defined quantum dots, are very similar to them. They haven't been scaled as much as these, but I'll just leave them here because numbers are pretty similar. Ion traps. If you look at the ion trap-based quantum computers, fidelities are even better. You can do even more operations per coherence time, right? Millions. They have excellent optical interfaces, but the problem is scalability. It's really hard to push this to a very large number of ions because you have to trap them near the structures and so on. Same problem holds for semiconductor quantum dots, where I actually spent more than 15 years working on them. These are indium arsenide quantum dots embedded in gallium arsenide. They have excellent fidelities, even larger number of 2-qubit operations than circuit QED systems, excellent optical interfaces. The best quantum light sources for quantum communication are based on these particular systems, but they're hard to scale for the reasons that I'll show you later. And then recently, these new systems have emerged, which are just based on impurities in diamond and silicon carbide, which are basically naturally trapped atoms, such as silicon inside of the diamond lattice. You all know that you can buy diamonds in different color, right? Pure diamond has no color. Color comes from impurities in it, right? So if you have different impurities, that will lead to different colors. We don't want them to be so contaminated with impurities that they change color, because we want to isolate and control individual impurities, but it's the same idea. We have impurities of silicon inside of diamond, and that's your naturally trapped atom that you use as your quantum bit, and then you process your device around that. And similarly, in silicon carbide, there are a variety of impurities, but the ones that we use are basically absence of silicon atoms. A silicon atom that's kicked out of the position, and that acts as your impurity. And if you look at properties of this, there are a lot of blank spots because we haven't done measurements on all of them yet. But we know, at least for the ones where we've done measurements, that fidelities are very high. Projected number of operations is in the millions, like for ions. They're fully scalable, and they already have excellent optical interfaces. We already know that, and we've demonstrated that. So this, I like to say, if this is a vacuum tube of quantum computing, and most likely it is, we already have 50-qubit quantum computer. That's where it is. We still need to look for a transistor, equivalent of a transistor. And equivalent of a transistor may be somewhere here, right? Because there is a limit to how far we can scale these ones, and they're pretty large. And in fact, they're getting even larger in an attempt to actually reduce the coherence. So now I'd like to spend, I think I have about 5 minutes or so, showing some of the work that we've done in this domain, and then wrap up by showing how the two parts of the talk connect to each other. So I'll kind of sweep through the part on quantum dots, and I'd like to show you more on the diamond and color centers and silicon carbide color centers, because that's where I think the future is. But quantum dots inside of the cavities have been the leading platform for quantum optics, and the best light sources for quantum communication are still based on these particular systems, right? So these are sources of individual particles of light, individual photons that you can use for secure communication. We've done work on that over many years, but if you look at this picture, you already see why these quantum dots are hard to scale, right? You grow them by self-assembly, molecular beam epitaxy, they're randomly positioned, their shapes and sizes vary, and as a result of that, these transition wavelengths, these emission wavelengths from them vary. And it's really hard to connect them to each other, right? So that's what has been preventing us from scaling the systems up further. So now I'll just skip through slides there and go to diamond, because this is all on quantum light sources. In the interest of time, just go to the second part. So if you look at these quantum dots, I showed you the picture of how one quantum dot looks like, and it looks very nice, narrow transition line. You remember probably from basic physics, spectral lines of atoms, right? That's what you need there. So when you look at one of them, looks like this. When you look many of them, looks like this. And that's very, very hard to scale and connect, right? Because they go all over the place because of the differences in individual atoms. So instead of that, now we're looking into these color centers in diamond and silicon carbide, which are in many ways very similar to quantum dots, but are better and more robust to the environment. So even when you look at the ensemble of them, spreading is not that large. So these 4 lines are a feature for a single color center, silicon impurity inside of diamond. And when you look at an ensemble of them, you will see the black spectrum. So not much broadening happening, only a few gigahertz, which is very, very easy to compensate and control. Similar for silicon carbide, again, broadening is very, very small. We're doing this in collaboration with Stuttgart, your Grachtrup's group. And what is also exciting is that the experiments on these materials could be done even at room temperatures. But everything works better when you cool it down, right? Because you isolate it better from the environment and lattice vibrations. But you don't have to cool it down to millikelvin temperatures. This is about 10 Kelvin. This one is room temperature, right? So there is a lot of potential there on building scalable systems. So for diamond, just to show where we are, right, we've managed in collaboration with a group of Marco Launcher at Harvard to incorporate these individual atoms inside of the resonators, because you remember these are optical systems. They have to interact with light. We see, I will not really go into details of these experiments because you are not really quantum optics experts. I'll just tell you what they mean, right? This means that you have individual atom, it emits 1 photon at a time, 1 particle of light at a time. So it's a good quantum light source. This tells you that it's not degraded when it's actually embedded inside of this resonator, when you have environment around it. And also, when it's embedded inside of this carved out resonator inside of the diamond lattice, you have much more enhanced light and matter interaction. You see that large enhancement in this its radiative emission rate. You see large enhancement in photoluminescence. And these are all signatures that we're looking for when we're embedding these atoms or artificial atoms inside of the structure. Even people who do microwave quantum computers, they have exactly the same things. They don't have atoms, but they have Josephson junctions, which are equivalents of atoms. And then they have microwave resonators. And they look for this regime where they interact strongly, which means that they are isolated from the environment. So we're in that regime for quantum dots and almost in that regime for color centers in diamond. And this is showing that presence of a single color center is changing transmission of light through the resonator, which means that you are in the right regime. With silicon carbide, same story. Single missing silicon atom inside of these structures is what is used as your quantum bit, right? And we have shown that we could manipulate the spin of that quantum bit even at room temperature and use optical signal for readout. So you could imagine that some structure looking like this, where each pillar contains one quantum bit and you can optically address them would be your quantum computer. And then you would connect them optically from the outside. So just to show you, again, results, you don't have to understand details. I'll just tell you what they mean. This tells you that these pillars are extracting your signal efficiently, optical signal efficiently. This is telling you that you have one atom inside of the pillar because it's emitting individual photons. And this is telling you that you are controlling spin of that electron inside of your color center precisely and using optical readout, right? So you have the ability to control single qubit inside of the pillar, and now you can go on to connect them. So just to finish this up, a lot of progress has been made with quantum hardware, right? And this is what pictures that I took from the slide I showed you before. But still, a lot has to be improved, right? And in like classical photonics, remember the first part of my talk, we still use very well-known structures, unoptimized structures, even for these devices, right? So this is the case certainly for optics, but it's not much different for microwave devices. The structures that they use for superconducting quantum bits in the computers that have been demonstrated are just traditional microwave strip lines and resonators, not really optimized, right? Just the same ones that you learn in your microwave engineering. They're trying to improve the coherence times or storage of these microwave photons by increasing these hollow metallic resonators, but not much optimization and design has even gone into that area. And for that reason, we also started wondering very recently whether we could use our optimization techniques or AI techniques to build better quantum hardware. Usually, people talk about the opposite problem. Can you build quantum hardware and use it to solve AI problems? And that's the whole field of quantum machine learning. Instead, the question that I think is more relevant right now is, can we use our existing hardware, AI hardware, and build better quantum computers and network them? So that was what I would like to leave, and just thank my group. These are the people who did the work. And of course, recent alumni, Jesse Liu, who started the work on inverse design. He's now at Google. Jan Petikiewicz, who is at Global Foundries, and Kai Müller, who is at TUM. And our support, including Samsung, who invested into our area through Systems X. Thank you very much for your attention.
Thank you. My question is maybe not exactly related to the methodology, although this is very interesting.
Yeah.
My background is security, and one of the things that I'm constantly being scared of being made scared of is the quantum resistance computing.
Yeah.
And just a highlight, what is it with quantum computing that make it make the traditional cryptography break so quickly?
Yeah, so the question is, what is in the quantum computing that threatens traditional cryptography? What threatens traditional cryptography is the ability to factor out large numbers very, very fast. And that's Shor's algorithm, right? So that, I didn't really talk much about it. In quantum computing, we actually have only few algorithms that are useful algorithms right now, right? Shor algorithm is arguably the most useful algorithm that people have come up with. It's Peter Shor, who is now at MIT. And that algorithm allows you to factor out very large numbers in polynomial time. And since all of the classical cryptography relies on basically factoring out large numbers, which is your secure key, that means that quantum computers would easily crack or decipher code for classical cryptography systems. Having that said, there is a lot of work on other classical cryptography protocols that people are doing at the moment that don't rely on factoring. And also, of course, if you have quantum cryptography systems, that would be resistant to any attacks by a quantum computer because it doesn't rely on the factoring. In fact, in quantum cryptography, you use quantum states of light to communicate, so any attempt to eavesdrop will be detected because you know that someone is messing up with your data. And you probably, even if you didn't take quantum mechanics, you know that when someone tries to measure a state of a quantum object, they mess up with the state of that object, right? So you know that something is happening, and you can see that someone is messing up with the system. You don't know who that is or anything, but you just know that something is going on. So you stop, and then you resend later on your cryptographic key, right?
So my question is actually, my question was, why is it that factoring is easy with quantum computing? That's the thing.
Why is it factoring is easy? That's well, I mean, all of the quantum algorithms are gaining the speed up based on the quantum superposition of states in quantum mechanical systems, right? So if you have your 100 quantum bits, right, you can simultaneously put them in all of the possible states of these bits, right? And then you can apply algorithm, and sort of that means that you, in a classical case, right, you have to run it for different inputs hundreds of times, right? In this case, you can put it in superposition state and run it for all of the inputs simultaneously, but you have to make a different algorithm. It's not a general purpose algorithm. There is a factoring algorithm. There is unsorted database search algorithm where the speed up has been proven, which means you know someone's phone number, you don't know who it is, right? How do you efficiently search the phone book, right? For that one, we also have a good algorithm. And there are some of the other algorithms where the speed up is not so dramatic, but they seem interesting. I mean, for example, this quantum machine learning, that's a growing field. Then a lot of interest is in optimization problems, but for that you don't need a general purpose quantum computer. Even annealer would work. It's a huge field of research, right?
I have a question. Look at your filter. Can you describe for me the material you use for that filter? The hole, I see it air.
Oh, for this,
yeah.
For this we use silicon. It's a silicon on insulator, right? So you just add SOI material, right, for these particular structures, which means, I mean, this is a commercially available, and it's also the same material that people industrially use for silicon photonics. So you have silicon substrate, oxide, and then silicon layer on top. But of course, if you would like to directly integrate it with electronics, you may not really want to have a different platform from the one that they already use for electronics. So we're looking at different, you can use one of the silicon layers and nitride or oxide and use that for your optics layer. But in general, it's just silicon with some oxide or nitride.
One last question. Photonic amplifier, very important. I wonder if the concept you use here can able to implement that.
Absolutely. I mean, you could, just a classical amplifier, you're talking about it. Yes, absolutely. I mean, you need some sort of gain. People have come up with Raman amplifiers, but also you can deposit some active material to increase the gain. Although, often you need amplifiers because you lose a lot of signal in classical circuits, right? So the idea here is that the losses are much, much smaller in these circuits, that it's not so critical to have amplifiers as much as in the classical circuits.
Okay, if you have other questions, you're welcome to come down and talk to our speaker. Thank you again for a wonderful talk.
Thank you.